My name is Paulo Refachinho. I obtained my PhD from Swansea University under the supervision of Professor Antonio Hill and Dr. Chung-Hin Lee. The title of my presentation today is Smoothed Particle Hydrodynamics for Fast Dynamics, from displacement-based formulation to first-order conservation laws. I will cover some groundwork done before I joined this research group, the key concepts for my own PhD thesis, and also some of our current efforts in this field. Before I start, I'd like to express my gratitude to the European Union's Horizon 2020 program, which supported my PhD research. I'd also like to thank the sponsor of the Roger Owen Award, River Publishers, and the organizers of the 2025 UKACM conference for making this opportunity possible. Thank you. I will start discussing some of the motivations and challenges behind this research, followed by a quick look at the classic displacement-based SPH formulation. Then we will explore conservation law-based approaches, numerical stabilization techniques, and explore some results and benchmarks. So, what exactly do we mean by fast dynamics? Dynamic events can be classified in several ways. For example, in terms of the differences in the geometry and materials of the targets and projectiles. Or another common classification is based on the characteristic velocity involved in the event. This figure illustrates a range of scenarios at increasing impact velocities, including the drop test of a mobile device, a bird and aircraft collision, ballistics, and the impact of space debris on satellites. What these cases have in common is that they represent high-energy events occurring in a very short time, from milliseconds to less than a microsecond. Inertia and wave propagation are important features of these events, and they often involve large deformations and potentially fracture. These types of problems have great economical importance, and improving how we understand them can lead to safer and more effective designs. However, experimental testing in these areas is expensive and challenging, which makes computational simulation even more important. But these are complex problems to simulate, and that's why we are here. The finite element method is well established and widely used in fast dynamics. For example, from impact penetration tests to a full vehicle crash simulation, finite element is the standard tool for many industries. However, there are some challenges that persist. For example, the time-consuming pre-processing of complex geometries, mesh distortion caused mainly by large deformations, which can compromise solution accuracy and may require adaptive remeshing, and the complexity of representing fracture, where some simplified element deletion methods can lead to very poor results. And then this naturally raises the question, are there any other alternatives? One promising alternative lies in the family of mesh-free methods, specifically the Smoothed Particle Hydrodynamics, or SPH. SPH was the first truly mesh-free method introduced back in the 1970s in the context of astrophysics, and later on adapted for solid dynamics in the early 1990s. It is a Lagrangian method, meaning it tracks individual particles as they move through space and time, making it especially well suited for solid dynamics. The core of SPH is interpolation theory. The main idea is to approximate a function using values at neighboring points weighted by a kernel function. A key concept comes from the shifting property of the Dirac delta function, which theoretically allows function reconstruction but is impractical for computations. Instead, we replace the delta function with a smooth kernel function, which vanishes beyond a certain radius of influence. Then, by applying particle integration, we approximate the integrals as summations over particles forming the so-called SPH formulation. Typical kernel functions include quadratic, cubic spline, and Gaussian functions. And just as we approximate a function this way, we can also approximate its gradient by computing the gradient of the kernel function. SPH has gained popularity since the 2000s, and communities like Spheric have identified the SPH grand challenges, with the first of them being convergence, consistency, and stability. This challenge is about managing unphysical energy modes, tensile and pressure instability, and the overall accuracy of the method. Our key contribution is a first-order conservation law-based SPH formulation, which offers a more stable and accurate alternative to classical displacement-based methods. By approaching SPH from this perspective, we can capture a wider range of physics and borrow established techniques from other fields such as computational fluid dynamics. As we will see in this presentation, the conservation law approach facilitates the understanding and the introduction of numerical dissipation to address the grand challenge number 1. Before diving into conservation laws, let's quickly revisit the standard displacement-based SPH formalism. Let's consider a solid body deforming from its initial state to a deformed configuration. This deformation is described by a mapping function phi, which gives the current coordinates in terms of the material coordinates and time. From there, we can compute velocities and the deformation gradient. In the total Lagrangian approach, we express the governing equations in the material configuration. For example, the equilibrium equation of solid dynamics states that mass times acceleration equals the divergence of the stresses plus body forces. To represent these stresses, we use the first Piola-Kirchhoff stress tensor, P, which depends on F, the deformation gradient. And how do we get P? So we link stresses and strains through a constitutive model. Once we have P, we use it to update velocities and displacements. Now here's something very important. The accuracy of F, especially in large deformations, directly affects the quality of the equilibrium solution. That is because first we solve the equilibrium equation to get velocities, then we integrate to obtain displacements. These displacements gives us F, the deformation gradient. F is fed into a constitutive model which gives us stresses. And finally, these stresses go back into the equilibrium equation. That's why many higher order or mixed-based formulations have been developed. The objective is to enhance this process. Now, let's look at how we would apply SPH to approximate the deformation gradient. The SPH approximation that I presented earlier, a few slides ago, for a generic function gradient, works the same way here. The deformation gradient is essentially the gradient of the current coordinates given by phi with respect to the material coordinates. And we can easily compute the gradient of the kernel function and use it in the summation over particles to approximate F. Mathematically, this looks similar to finite element shape functions. We basically multiply a kernel gradient by a volume term. To improve the accuracy, we introduce a standard correction that modifies the kernel gradient by a correction matrix L. This is indicated by the tilde over the gradient symbol here. The use of this correction will ensure that the gradient of any linear field is exactly evaluated. We also artificially introduce the minus phi a term to ensure that the gradient of a constant function will vanish. Finally, we can see this from a finite volume method perspective. In SPH, we don't really have faces or areas. We are dealing with particles, but we can introduce a pseudo-area vector by normalizing the kernel gradient with the particle volume. And later on, this will allow us to adapt an upwinding stabilization technique, a method commonly used in CFD, to SPH. We can now write the principle of virtual work, where the term on the left-hand side represents the virtual work of inertial forces, and the terms on the right-hand side represent the virtual work of external and internal forces. We apply particle integration for each of these terms. For the inertial and external forces, this is straightforward. But for the internal forces, we need to approximate the gradient of the virtual velocity field using SPH. So rearranging this expression gives us a term for the evaluation of the stress-induced interaction force between particles. Putting it all together and recognizing that this holds for any arbitrary virtual velocity field leads us to the discrete form of the dynamic equilibrium equation. In SPH, particles also act as quadrature points, meaning that they carry the physics. Just like in reduced integration for finite elements, we often need to add numerical dissipation. However, in classic SPH, finding the best way to introduce stabilization is not always user-friendly. A common approach is to add artificial diffusion terms, often based on second-order derivatives, such as the Laplacian operator. And these techniques help to control instabilities, but they can be very tricky to tune or to apply effectively. This challenge is one of the key reasons why we transitioned to a conservation law-based formulation, which we will explore now. So let's now switch to a conservation law-based formulation, and the goal is to improve accuracy, facilitate the coupling between different physics, and also introduce a well-established stabilization technique. We start with the standard form of a conservation law. On the left, we have the rate of change of the concentration of a physical quantity. For example, if this physical quantity was mass, Ux would represent the density. The first term on the right-hand side measures the amount of the physical quantity that enters or leaves the volume through its surface. This is known as the resultant surface flux, Fx. And finally, the last term is the global or resultant source term, which measures the amount of the quantity introduced or removed from the volume per unit time due to any known external sources, Sx. We can write this equation locally using the divergence theorem on the surface term and assuming the volume omega x doesn't change in time. And for situations with discontinuities, we also have the associated jump conditions. Notice that the domain of integration here is the material domain, giving us a total Lagrangian conservation law. We can easily transform this to other configurations. So let's transform it from total Lagrangian to an updated reference Lagrangian representation. So let's consider again the motion of a solid body, described by a mapping phi and a deformation gradient, f. And then instead of working only with the material configuration, as we would do in a total Lagrangian approach, or the spatial configuration, as in an updated Lagrangian approach, we can actually introduce an intermediate reference configuration. This is done by decomposing the deformation into internal and incremental deformation variables. This allows us to describe the system in terms of this intermediate reference configuration, rather than a fixed material domain. If we apply a standard push forward to the total Lagrangian surface integral using the cofactor of the internal deformation gradient, or the Nanson's rule, and then a push forward to the volume integral using its Jacobian, we obtain an equivalent conservation law expressed in terms of the intermediate reference configuration. From here, we can once again derive the local form and the associated jump conditions. Our goal now is to cast the equations of motion for solids into this conservation law form. Basically, this translates into writing a conservation equation for the linear momentum, balancing internal stress forces and external body forces. Here we have the total Lagrangian form, which can then be transformed into an updated reference Lagrangian version. We also introduce the deformation gradient as a primary variable and derive its evolution law. This equation has no external source term, only a simple surface flux dependent on the velocity. And again, we can start with the total Lagrangian version, which can then be transformed into an updated reference Lagrangian form. Having the deformation gradient solved along with the linear momentum as a primary variable of the problem avoids the reduced order of accuracy often observed for stresses and strains in displacement-based methods. Finally, if we want to capture thermomechanical behavior, we can optionally extend the system by including the first law of thermodynamics, here expressed in terms of the entropy, and this will allow us to model temperature evolution as well. Here is the total Lagrangian version of the set of equations in a compact form, and the updated reference Lagrangian counterpart. With both forms side by side, we can clearly see how similar they are. However, we should note that the updated reference Lagrangian introduces a new reference configuration that can be updated as required. So how exactly is this reference configuration defined? Let's look at this from a time-discrete perspective. And at the initial time, t0, the reference configuration matches the initial geometry of the problem. And the internal deformation variable is simply the identity. At this stage, we compute the kernel gradients for our SPH approximation based on this reference configuration. Then, as we advance in time, we solve for the incremental deformation variables. Since the reference remains unchanged during these steps, we don't need to recompute the kernel gradients. And this is exactly how a total Lagrangian simulation works. After several time steps, we can update the reference configuration to match the current deformed domain. And when this happens, we must recalculate the kernel gradients to reflect the new geometry. So from this updated reference configuration, we continue solving for the incremental deformation until the next update. This update process can be arbitrary, or it can be triggered by physical events such as a plastic strain threshold or fracture. Before we look at the discretization of the system of conservation laws, let's introduce the concept of ballistic energy, which combines kinetic energy, internal strain energy, and heat in a single equation. From this expression, we derive the word conjugates for momentum, deformation gradient, and entropy. And then to obtain the weak form, we start by multiplying the system of conservation laws by the virtual energy conjugates. Next, we integrate by parts, which is crucial because it will allow us to impose boundary conditions naturally. Then we apply particle integration, where the SPH approximation will be used to compute the gradient of the virtual fields. As before, we can apply corrections to ensure exact reproduction of constant and linear functions, and then we arrive at the final discrete form of the system of conservation laws. Expanding this system, we obtain the discrete equations for linear momentum, deformation gradient, and entropy, all written in terms of the updated reference configuration. But we are not done yet. Even with this conservation law approach, this is still SPH that uses particle integration, which means it is under-integrated and numerical stabilization is still necessary. So let's keep this dissipation term in mind because we will come back and derive it soon. The goal is to introduce dissipation to eliminate instabilities, for example, zero energy modes, without excessive damping or violating the underlying physics. And ideally, we want to do this without relying on case-dependent artificial parameters. We begin by recalling the second law of thermodynamics by differentiating the ballistic energy with respect to time and applying the chain rule. We can expand the expression to combine the rate of change of momentum, deformation gradient, and entropy. After substituting the corresponding conservation equations and simplifying, we can group together the power of the external forces, pi external, and the heat exchange terms, Q external. The remaining term represents irreversible heat flux due to conduction, which is modeled using Fourier's law. As we know, heat will flow from hot to cold, and therefore we can express this relationship as an inequality to ensure non-negative entropy production. Finally, we can derive the stabilization term, and we will begin with this semi-discrete version of the second law. After substituting the conservation equations and rearranging, we end up with an expression that's very similar to what we had in the continuum form, but with this added dissipation term. This is the same term that we introduced in the momentum equation a few slides ago. To ensure non-negative entropy production, and thus satisfy the second law of thermodynamics, we need the term inside the square brackets to be positive. By observing the local conservation nature of this pairwise stabilization term, we can express it in a way that directly relates to the jump or the difference in velocity between particles. Now we have this dissipation term d, which still needs to be defined, and the sufficient condition to satisfy the second law of thermodynamics is to define d in terms of a positive definite stabilization matrix that I'm calling S here. So in this work, we explore a stabilization matrix based on wave speeds, both pressure and shear, projected in the normal and tangential directions. This approach effectively dissipates some physical oscillations without relying on any artificial case-dependent parameters. Moreover, for many constitutive models, we can derive closed-form solutions for CP and CS, making this method both robust and flexible. Now I'd like to present a few benchmarks and examples. And the first example demonstrates second-order convergence using a manufactured exact solution. We perform particle refinements and plot the L2 norm error for linear momentum, stresses, and temperature. And all three quantities show second-order convergence. In the next example, we have a nearly incompressible twisting bar where the material's Poisson's ratio approaches 0.5, making the problem even more challenging. This example has been widely benchmarked by many authors and involves a squared cross-section column subjected to a twisting dynamic load. The column is twisted using an initial velocity field with an angular velocity of 105 radians per second at the start. The bottom face is then suddenly clamped, causing the torsion of the column. Here I'm showing the pressure contours for 3 different formulations: the updated reference Lagrange formulation, the total Lagrange formulation, and a conservation law-based formulation implemented in vertex-centered finite volume in OpenFOAM. On the far right of this figure, you can also see the result from a classic non-stabilized displacement-based SPH formulation, where pressure instabilities are clearly visible. Now, let's look at a more complex example: an elastoplastic bar undergoing rapid stretching, which causes the necking at the midsection. I want to show you an animation comparing 3 different formulations. On the left, we have the classic displacement-based formulation, which experiences pressure instabilities at the necking region. In the middle, the total Lagrange formulation solves the problem but is less accurate in describing the necking behavior as the simulation progresses. On the right, the updated reference Lagrange formulation provides a more accurate representation of the necking phenomenon. It's very important to note here that this is not a fracture simulation, so these gaps between particles result from extreme stretching. In a real-world scenario, the bar would eventually fracture into 2 parts. However, our goal here was to push the formulation to its limits and evaluate the performance under severe tensile deformation. This example is also important because it demonstrates how our updated reference Lagrangian SPH methodology can mitigate spurious modes often encountered in traditional updated Lagrangian SPH, especially in problems like this involving massive stretching. We accurately capture the onset of the necking with very few particles, and we solve the post-necking deformation behavior effective without introducing no physical hourglass modes. Now, let's look at a more practical application: a soft robotic gripper undergoing thermoelastic deformation. The gripper has 4 flexible arms attached to a hollow hub. It is made of a nail-hooking material with nearly incompressible behavior, and the deformation is driven by a constant traction force at the arm ends, combined with the heat conduction due to the temperature difference between the hub and the arm ends. In this case, our SPH formulation captures the interaction between thermal expansion and mechanical deformation very accurately. We observe smooth pressure and temperature distributions, even in this bending-dominated large deformation scenario, which could be challenging for other formulations. In this next example, we apply the SPH algorithm to a simplified cardiovascular stent with a thin thickness. The goal is to study its deformation under a time-varying velocity field. Using a nail-hooking material with nearly incompressible properties, the simulation captures the deformation even with minimal particle refinement. In this case, the pressure is well modeled, even though we have just 2 particles across the thickness. And as you can see from this other version of the stent, the complexity of the geometry doesn't pose any limitation. So this demonstrates that the methodology can be effectively applied to a range of fields. Now, in an example similar to the necking bar, but loaded in the reverse direction, we examine the impact of a copper bar against a bridged wall. This is a classic benchmark with very well documented experimental data. It goes usually with the name Taylor bar, Taylor impact bar. The bar impacts a ridged wall with a velocity of 227 meters per second. Here I'm showing the evolution of kinetic, strain, and plastic energies, showing how most of the kinetic energy is rapidly converted into internal strain and heat. We also monitor the impact radius, which matches the experimental data, and the performance will improve with particle refinement. The updated Lagrangian results show excellent agreement with the total Lagrangian SP8 algorithm, and the simulation captures smooth pressure and temperature profiles, highlighting the ability to handle high-speed impacts and large plastic deformations. As a final set of examples, I'd like to show some ongoing work on dynamic brittle fracture. One important point to keep in mind is that in mesh-free methods, a continuous crack will likely be represented as a group of contiguous fractured particles. To model this kind of behavior, there are a few key ingredients that we need. Number one is a failure criterion to determine when fracture occurs, such as the Rankine criterion, which defines a threshold on the maximum principal stress. Number two is an updated formulation of the equations, and this is where the updated reference Lagrangian SPH formulation that I just presented becomes especially useful. And finally, a post-fracture model, such as a traction crack opening law, to describe how the material behaves after failure. To keep things simple, we can start with a linear cohesive law tied to the Griffith fracture energy. With this simple initial approach, we have already been able to reproduce crack patterns from classic dynamic fracture benchmarks quite well. In this first example, we demonstrate the prediction of dynamic crack propagation in a beam with an offset edge crack subjected to an impact load. Crack propagation is driven by the Rankine criterion, and here I'm showing both the crack pattern and the maximum principal stress at the crack tip. In this other example, we model crack initiation and propagation in a notched plate with a hole. The load is applied by a top beam and the plate is fixed at the bottom. The hole offset from the center induces mixed mold fracture. The material used is a cement mortar, and the crack trajectory observed in the experiments can be successfully predicted by the numerical simulations. This is all preliminary work that we've been developing in the past few months. We are now investigating more detailed comparisons, focusing on parameters such as the crack tip propagation speed and the energy release rates. So these analyses will offer deeper insights into dynamic fracture, allowing for more comprehensive understanding of fracture behavior and the verification of our models. That brings me to the end of my presentation. I've covered some of the key challenges we face with SPH, especially around convergence, consistency, and stability. I also introduced a potential solution with the conservation law-based formulation. The main feature of this formulation is its mixed-based set of first-order conservation laws, which improves the accuracy of the stresses and strains, while also enabling the inclusion of other physics like thermal effects. Plus, the structure of the system makes it compatible with well-established stabilization techniques. This framework works really well for problems involving large deformations, thermoelasticity, elastoplasticity, and now we are expanding it to tackle dynamic fracture. I will stop here, leave you with some key references, and I'm happy to take any questions. Thank you.